Let's use the relative dating principles that you learned in the last video to figure out how these geologic features came to be. Here's our outline. So far, we've only looked at the first bullet, the 7 stratigraphic principles used in relative dating. We'll do a little review of that, and then we'll go on to the rest of the outline. I thought that first it would be a good idea to think about watching these events occur from the oldest to the youngest and seeing what we end up with at the end. Here we have 4 sedimentary rock units that have formed. The oldest is a conglomerate, A. Then we have a sandstone, B, a shale, C, and limestone, D. Oldest on the bottom, youngest on top, principle of superposition. Also, principle of original horizontality and lateral continuity. After these are deposited, we then have a sill intrude between units C and D. That's shown here as E. If there were inclusions in E of D and C, that would help us even further know that this was a sill. The next event to occur was the intrusion of a dike, F. Then we have something called an unconformity, which I haven't talked about yet in these videos, but I will in just a few minutes in this one. An unconformity is basically a surface where erosion has occurred and removed rocks. It basically represents missing time. It could represent a couple thousands or millions of years or even hundreds of millions of years of missing time. In this case, we've had these units wholesale tilted. You can see that they're all horizontal here, but by this time they're all tilted. And then we've had this erosional surface created at the top. Sometime later, we had the deposition of the last 3 units, H, a conglomerate, I, a sandstone, and J, a limestone, being the youngest unit. Again, these are showing the principles of original horizontality, lateral continuity, and superposition. As shown here, a river comes through and eventually erodes enough so that we can see some of these units. As you can see, if you don't know what's going on at depth, it's difficult to put together the entire story. So let's look at the example we started with. What do you think are the oldest rocks or events in this picture? Notice that the metamorphic rocks, which are this folded pattern, and unit B, which is a pluton, are the lowest units in this diagram. So from the principle of superposition, it's quite likely that these are the oldest units. There are some other things down here as well, though. There are some faults and a dike. But notice that the fault, F, and the dike both cut through these 2 rock units. So the rock units must be older than the fault and the dike. That is the principle of cross-cutting relationships. How can we tell which came first, the metamorphic rocks or the pluton B? Well, we have one more thing that can help us, and that is the fault A, shown over here. Notice that the A fault does cut the metamorphic rocks, but it does not cut the pluton. In fact, the pluton has cut the fault. So again, from the principle of cross-cutting relationships, we have information. Fault A cuts the metamorphic rocks. Fault A is cut by pluton B, so the fault is younger than the metamorphic rocks, but older than the pluton. So we're going to start a list here on the left from oldest to youngest. So now we have metamorphic rocks as the oldest event in this picture, fault A, and then pluton B is the youngest in terms of those 3. Let's move on. Now above all of these features, we see an erosional surface, which is this kind of jagged line here. So erosion must have occurred next. Then we have unit C that's deposited on that erosional surface. We notice that it's cut by fault F and it's cut by the dike. So it must be older than these 2 features. Deposition of unit C. Now, how do we know what's older, fault F or the dike D? Well, let's look at the unit E. Unit E is cut by the fault, but the dike does not pass into unit E. So unit E is younger than the dike and older than the fault. So let's add those to our list. So now we had erosion, deposition of unit C, the dike cuts through, then deposition of unit E, and then finally fault F cuts everything in the picture and is the youngest. So that's how we play this game. Okay, let's continue with our outline. Fossil succession. Fossils, of course, represent the remains or the traces of animals and plants from the past. These are useful for helping us figure out relative age determinations. Paleontologists who study fossils have realized that species evolve, exist for a certain amount of time, and then disappear from the fossil record forever. Their first appearance and their final extinction date gives us the range of their existence, and that can help us for relative dating. This is shown over here in this diagram where we have a number of fossils, the oldest being down here, the youngest up top. So this oldest fossil, for example, is found in units 1 and 2. Fossil B is found in units 2 and 3. C is in units 3, 4, 5, and 6, and so on. So if we know the order of these fossils in other locations, they can help us in new locations. If we happen to know the age constraints on a fossil, let's say fossil D was around only between 200 and 190 million years ago, and we find it in a rock, well then we know that that rock unit is between 190 and 200 million years old. The successive change of the fossils as time goes on is where the concept of fossil succession comes from. Here's another way to look at it. Here's the geologic timescale on the left, the Paleozoic, Mesozoic, and Cenozoic, and we have different ranges of fossils coming into existence and disappearing from the rock record. This line here represents the Permian-Triassic extinction event. You can see a lot of organisms disappeared. But let's say we have a rock unit that has a Eurypterus fossil, a Phacops fossil, and a Rhodocrinites fossil. Can we say anything about the age of that rock unit? Yes, it must be Devonian, because this is the only time period when all three of these were around. Unconformities. An unconformity is a time gap in the rock record, either from a lack of deposition or erosion or both. Here we have a surface that was eroded, and who knows how much time there was in between the next unit being deposited, but eventually this was all tilted as well, because usually unconformities start out horizontal. There are three kinds of unconformities. An angular unconformity is when horizontal strata are on top of tilted or folded strata that are below them. Here's a picture showing what happens. We have some mountains that are forming with some sedimentary rocks. We have compression from tectonics, and then we have this future erosional surface, which gives us time 2 with these folded rocks below. At time 3, we have new horizontal sedimentary layers, and now our angular conformity is located here between the two of them. James Hutton, who we talked about in the last video, was the first person to recognize the significance of angular unconformities and that they represent huge amounts of geologic time. This is a photo as well as a sketch from the place in Scotland where Hutton figured out the significance of angular unconformities. The rocks on top are called the Old Red Sandstone, and they're tilted gently. The rocks underneath, which are kind of hidden, but you can see better here, are a sandstone that are vertical. The time between the deposition of the sandstone on the bottom and the one on the top is 50 million years. So what happened? This sandstone over here was deposited horizontally. It was then tilted almost to vertical, eroded, and then a new sandstone deposited horizontally. Since that time, everything's been tilted a little more again. Here's another example. We have some highly tilted beds here, and the angular unconformity between them tells us about the timing of the uplift of the Appalachian Mountains. Nonconformities involve igneous or metamorphic rocks that are capped by sedimentary rocks. Here we have a granite, and then there was an erosional surface, and then a sandstone was laid down on top of it. We have a granite, which we're indicating with this kind of hatch mark pattern, and then there's an erosional surface that's created. This is time 2, where we have that erosional surface, and then in time 3, we have more sedimentary rocks pile onto it, and this is what we call a nonconformity. Finally, there are disconformities. These occur within sedimentary layers. Here are a bunch of horizontal sedimentary layers, but there's a new erosional surface right here. That erosional surface is shown here as the ground surface. And then when new sedimentary rocks come in, we have this disconformity where that break in time was. This shows sediments from a channel that scoured into underlying layers of sedimentary rock. Here's a summary of all of these different kinds of unconformities. Finally, stratigraphic correlation. We can use the information that we've discussed in these two videos to correlate from locations that are far away from each other. Here, we're using the assemblage of fossils in two localities to correlate them as being the same age. This image shows rocks from 3 different areas. We have rocks from Bryce-Cedar Breaks National Parks in Utah. Here we have Zion Canyon in Utah. And here we have the Grand Canyon in Arizona. In Cedar Breaks and Bryce, we have rocks ranging in age from Tertiary through a little bit of Triassic. The Navajo sandstone at the base of this section is at the top of the Zion section, which has Jurassic, Triassic, and Permian rocks. The base of the Zion Canyon section has the Kaibab limestone, which is also in the Grand Canyon. So last time I showed you this, we can correlate all of these areas and come up with a large stratigraphic section for this entire area. Okay, so we're going to wrap up with one last question. How did this particular set of geologic relationships form? I want you to put on pause and try to think about what happened first, what happened second. See if you can put this all together. I'll give you a few pointers. Unit 1 is a sedimentary rock called limestone. Unit 2, 4, and 6 with this gray stripy pattern are shales, sedimentary rock. Units 3 and 5 are sandstones. There's a sill shown between units 4 and 5 with inclusions of both this 5 and number 4. There's a granite pluton, and there's pieces of unit 5 within it. There's a fault, and there's a dike. So see if you can figure out what was the oldest all the way to the youngest. Okay, let's look at the answer. First, we had deposition of units 1 through 7. I'm not sure why there's a unit 8 here. I didn't make these figures, but deposition of all of these sedimentary rock units came first. Then we had the intrusion of the sill. This was followed by folding. There was a magma intrusion, which created the pluton. There was normal faulting. There was a dike that cut across all of these features, leading up to a volcano. And then the volcano and other things on the surface were eroded. That's our final picture. You can see how walking over the land surface only gives you part of the geologic story. That's it for stratigraphy. I'm going to finish up here with my favorite Zitz cartoon, and that's it.